Alright, I'm forgetting something, but I'll remember it once I stop forgetting it. Maybe. Alright, yeah, Perseverance landed. That was cool. That never gets old for me. I was a NASA kid. I grew up in the 60s watching the Apollo missions, and remember sitting in front of the TV set when they were landing on the moon during Apollo 11, and that was just crazy to watch. And the stuff we're doing today is no less impressive. So yeah, it's good stuff. All right. Any questions so far? We dug deep into recursion yesterday, and talked about recursive tree traversal. We did recursive search and insert, and we started to talk a little bit about deletion. Let me see something. Oh yeah, there we go. Okay, we'll play with that later. All right. Well, let's play with. Yeah, question. All right. Let's look at deleting from a binary search tree. And so you know, basic setup, you got a tree and you want to delete a node. Well, if you want to delete a leaf node, right, that's pretty easy. Just, you know, get rid of it and change its parent to point to null. That's not a problem. But it's more complex if you're trying to delete a node that's, you know, in the middle here. Because if I delete this, I can free it from memory. But who's going to point to this node? How do I ensure that this whole subtree is not lost? And, you know, I could have the root node point to that, but then who's going to point to this node? So we have to do some work to remove a node from a tree. And so we're going to use recursion again for most of that work. And so our basic setup's going to be the following. So there's an arbitrary tree. Let's say we want to delete the 47. We're going to do this recursively. We're going to say 47 is sitting in this subtree, so hey, let's use this fancy delete algorithm and remove a 47 from this tree. And then we'll just make this tree the right subchild of the root. And we're done. And if we want to delete, you know, 5, we'll say, hey, 5 is somewhere in this left subtree. Call my fancy delete routine to delete 5 from here, and then make the left subchild of 20 that tree that we've deleted the 5 from. So mostly delete is going to be recursive. So it's going to look like this. So take a number and take the root of a tree and let's delete it, and we're going to return the root of the tree that results from deleting this number from that rooted tree. So if our number is less than our root, then we're going to say root left equals delete. So delete from the left subtree our number, take the tree that results, have root point to that on the left, and then we're just going to return root. I hope everybody saw my note about the typo yesterday during lecture about how to insert, but we're going to play with insert again, so we'll clarify that. So if our number is smaller than the root data, delete it from the left subtree, point to that from your root on the left, and return the root. If your number, on the other hand, is bigger than the root data, then recursively call your delete function to delete from the right subtree the node containing your number, and have root point to that new tree on the right, and return your root. So those two steps are pretty easy to write. We don't actually do any work. They're just recursive calls. Our third case is the tricky one, which is where the number we're deleting is at the root of the tree. And in some sense, this is the worst scenario. We're trying to delete the number 20. Well, we can find it really easily. It's just this node right here. But if we delete that, we have all of this stuff that's been orphaned right now. The parent of this tree and the parent of this tree has just been deleted and freed from memory. So how do we maintain a viable tree that lets us get to everything? So deleting the root is the trickiest part. And we're going to use the following algorithm. We could switch back to a linked list, but we're not going to go backwards. We want to stick to a tree. So here's our basic approach. To delete the root of some tree T, we're going to find the largest node in the left subtree, so T dot left. And we're going to make that node the root. So if we want to delete the 20, what we're going to do is we're going to go into the left subtree, we're going to find the largest node, which is a 12, and we're going to make that node the root of the tree. Now, why are we allowed to do that? Alright, here's our original tree. The largest node in the left subtree is 12. So this is T. So everything to the left of the root is smaller than the root. If 12 is the largest node in this subtree, it means everything in this subtree other than 12 is less than 12. So if we move 12 up to the root and we put everything else to the left of that, we're still satisfying the BST property, that everything to the left of the new root is going to be less than it. So that will preserve the fact that this is a binary search tree. The other thing to note is that 12 has no right child. And how do we know that 12 has no right child? Because it's the largest node in this subtree, and anything to the right of 12 would have to be bigger than 12, which means 12 would not be the largest thing in that subtree. So because 12 is the largest node in the left subtree, it has no right child, so 12 is totally free to adopt on its right the original subtree on the right of the root. So that's all fine. And then on the left we have our other tree. But what if it had a left child? So let's make a slightly different version of this. So we've got a 20. We're not going to worry too much about what's on the right. But let's look at the left. So there's a 10, and there's a 5, and there's a 12, and suppose there's an 11 hanging over there. So if we move 12 up to be the root, it adopts all that stuff. We've got the 10, we've got the 5, but 12 already had something on the left. So that 11 is going to go right here where the 12 was. And the thing immediately to the left is the largest thing in this subtree to the left of 12. And since 12 is moving up, if we basically move that up to here, we'll still maintain the property that it's a binary search tree. So it becomes the child of 12. So what does this look like in a more complex example? Right, so there's an example of a binary search tree. And if we want to delete the 20, we're going to take the largest thing in the left subtree, that's a 15, and we're going to make that the root. So the 15 is going to go up here to become the new root. 15 will adopt all of this on its right, and its left child will simply move up and take its place. And it'll be adopted by 10 in this case. So this will end up looking like 15, 40, and all the stuff on the right subtree, and then 10 and 5 and 2. And the right child of 10 will be everything that was to the left of 15. So this will be 13, 14, 12, 11. Excellent question. So our full algorithm to delete the root of t, find the largest node in t left, so let's call this node n. Make that node the new root, and then have n's parent adopt n's left subtree on its right. In other words, move n's left subtree up in place of n. Yeah, that's pretty whack. But it's not too bad to code. If we're comfortable with using temporary variables, this is not too bad. So how would we engineer this? We have our original root. We have the left subtree. We have to find the largest thing. Well, how do we do that? We basically want to try moving as far to the right as possible. So come down here to, your left subtree, start of the root, and just keep moving as far right as possible. And we're going to use the same current previous idea. And when we can't go any further to the right, then current will be our largest node, and previous will be its parent. So let me do a slightly more interesting example. So here's our root, which is 20. with a bunch of stuff hanging off to the right. Here's a 10. Here's a 12. Here's a 14. Here's a 20. Here's a 16. There's a 17. There's a 19. There's an 18. Here's a 15. Alright, big old messy binary tree. And so let's see how we delete the 20. So we're going to start at the root. We're going to come down to the left and we're going to explore this left subtree. And the idea is I'm going to start moving to the right. And I'm going to use a previous current pair of pointers. So I'm going to start off with here's my current node. And if it has something to the right, I'm going to set previous, let me just call it P for previous, equal to that, and current equal to previous next. And there's something to the right of that, so I'm going to change this to previous and this to current, right? So we're doing linked list traversal. And I'm going to, are there two 20s? Oh, okay. There we go. Thank you. All right. So there's the previous and the current. There's something to the right of that. So move down again. Here's the previous and here's the current. And now there's nothing to the right of that. So I know that current is my largest node in my left subtree. So C equals largest node in left subtree. P equals C's parent. All right, so what do we do? C is going to become the new root. So C right equals root right. So that changes C to point to all of this stuff that's sitting on the right. All right, C's left child is going to become whatever the root's left child is. So now C on the left is going to point to this whole subtree. But before we do that, we have to make sure we don't orphan C's current left child. So before we change C left, we're going to take C's parent node, and it's going to lose its right child, which is C, so instead it's going to adopt C's left child. And then C left will become the root, and then we're going to free the root, and then we're going to return C as the new root of the tree. All right, this is one of those points where we really don't want to be thinking too much about, pointers and ampersands and stars and fields within and that kind of stuff. We want to be thinking about this from a higher level, right? This is the pictures that I keep referring to when we did linked lists and when we started working with trees, right? If I understand, this notation, right, this is a direct representation of the steps that we've just described, right? Have this be the new root, which means its right child should be everything that's to the right of root. That's that statement. Have its parent, P, adopt C's left child on its right, so P right is C left. Have C, as the new root, adopt everything that was to the left of the old root, so C left is root left. Free the root, that's just free root, and then since C is the root of the tree, and our delete function is supposed to always return the root of the tree after the deletion, right, we just return C. And there's more edge cases on top of this, right? One edge case is the situation where you have something like this. We're deleting the 20. The largest thing in the left subtree is 10. Well, doing this business of previous current, right, and looking for the parent of 10 is not going to work. This is an extra case. But again, what we want to do here is we want to take 10, we want to make that the new root. And on its right, it's going to adopt, you know, the old right subtree of the root, and on the left, it's going to adopt the old left subtree. So this is going to turn into 10, 40, 5, 3, 6. So you have to be a little careful with this business. In the case where there's only one node here, where this is the largest thing in the tree, there's nothing to its right. If we try to do this previous current, we don't know what to set previous to. So that's a condition you have to check for, right? But it's basically, you know, checking to see if the root of the tree has nothing to the right. The other condition, of course, is if there's no left subtree at all. If this is our tree and we want to delete the root, there is nothing to the left. We can't find the largest node in the left. So what do we do? Well, deleting the 20 from this tree is easy. Boom, it's gone. So new root equals root right. Free the original root. Return the new root. So that's our other edge case. All right, so questions about that? So this is your main algorithm. But again, just like with so many other things, right, I don't want you to memorize this. I don't want you to marry yourself to this. I don't want you to code this and be wondering, you know, why am I doing this? What does this mean? I want you to come up with this. I want you to understand the algorithm, which is find the largest thing in the left subtree and make that the new root. And from your understanding of that algorithm, I want you to come up with this code. And it might look different from this. That's fine, right? But I want it to make sense to you because it's an implementation of this algorithm we're describing, which is replace the root with the largest thing from the left. right, questions? So even though I said, leave this as the last part for PA4, right? You've seen tree code for inserting integers into trees, and you know how to write, recursive traverse functions. It's 4 lines, so that's not bad. I would suggest going ahead and before you go too deep into PA4, particularly before you get to the delete, try to do this with just a plain old tree of integers. And start playing around with this delete function on integers. Forget about, the license plates and first name, last names, and dynamic allocation. Forget about memory leaks for now and all that kind of stuff. Just think about how you do this delete algorithm. And one of the trickier spots is finding the largest node in the left subtree. And how do we do that? Well, we can find the left subtree. That's just root arrow left. So how do you find the largest node in a tree? Well, you could write a function for that. And basically, you just move as far to the right as possible. So start from the root, move right, move right, move right. When you can't move right any further, you have found the largest node. And as you're moving right, keep track of the node that you were at before. That's your previous. So that when you found the largest node, you know the identity of its parent. And before you do any of that in a loop, check to see if the root has anything to the right. And if it doesn't, that's an edge case. That's an edge case where this is the largest, and it has no parent to adopt, its left child. But in fact, the left child is going to become the left child of the root. So there's a few cases to worry about in there. And this is going to be an increasing theme is we're going to see algorithms with more and more special cases where, what we do is going to depend on which of 5 different scenarios we're in. And so we want to increase our comfort with, being able to code different sections of an algorithm saying, if this is the case, let's do these things. If this is the case, let's do those things, and so on. And this will come up when we talk about balancing trees, which we're coming to soon. Alright, and this is the algorithm you have to use for PA4 to get full credit for deletion. So if I was to delete the 20 from this tree, what would I do? I would go into the left subtree, I'd find the largest node, which is 17. I would make 17 the new root. It would adopt the old left child of the root. And if 17 had something on the left, like 16, that gets adopted by its parent. For some reason, when I've given this type of assignment in the past where people delete the root of trees, about half the class does the following. They look and they say, oh, there's only one node on the right, so I'm going to make 30 the root. And they just move 30 up to there. That's a valid tree deletion, but it's not the algorithm we're after. And inevitably what turns out to have happened is somebody looked up an algorithm on Stack Overflow or something, and it got passed around the class, right? So always take the largest thing from the left subtree, move that up to the root. The only exception is if there is no left subtree. And in that case only, right, we just change the root down to the right child of the original root. And this is one of two possible deletion algorithms. A perfectly fine alternative algorithm is to replace the root with the smallest thing from the right subtree. It works exactly the same. Just stand in front of a mirror while you're coding, and you've got the exact same behavior. The smallest thing from the right subtree has the same properties that, everything else in this tree is bigger, so if we make that the root, it's still a BST, etc., etc. And how do you find the smallest thing in the right? Move into the right subtree and move as far left as possible. And when we move that to the root, if it had something on its left, that'll be adopted by its parent, and so on. All right, but for PA4, use the first algorithm we described. Take the largest node from the left, make that the new root. Coding in front of a mirror would be interesting, especially if you rely on looking at your keyboard. Although mirrors have that funny thing, they swap left-right, but they don't swap up-down, which is kind of cool. And you've seen my mirrored display, so no surprise there. All right, so let me correct our insert routine from yesterday. So we were doing recursive insert. So insert a root and a number. And we were writing cases like, for example, if our number is less than the root's data, and we want to insert into the left subtree. And I think I said we return this. That's not correct. Okay, so this was an error. If we're inserting something smaller than the root of the tree, we want to insert into the left subtree, but we need to take the result of that and make that the left child of root. So here's our tree, and we insert, I don't know, 13. Okay, go into the left subtree, insert a 13, and then make your root point to that on the left. And then just return the original root. And since, the tree is not null, because if the tree was null, we wouldn't have gotten here. We would have already created a new node and so on. So since the root is not null, the root is never going to change when we insert, right? If this is the root of the tree that we're being sent, we're going to make changes over here or over here, which could potentially change the left child, or it might not, but the root's still going to be the original root. So we need to do this and then an identical thing on the right. All right, so let me see if this is doable. So I have some really tiny code here, or maybe some really big fingers. All right, so this is, let's see, so what are we using to determine the value of a node in PA4? These examples are with ints, but PA4 is license plate. So the license plate is the key. So you're going to use the plate, and then use string compare to compare two things. And string compare A comma B, it returns something positive if A is larger than B, negative if A is less than B, and 0 if A is equal to B. So use that for your comparison instead of just greater than, equal than, less than. All right, cool. All right, so let's do some tree insertion. Well, I hadn't thought about writing this small. Let's insert a node into a tree. So I'm going to do an insertion into an empty tree. So my root is going to be null. And this is page 1, and this is called from main. And I'm going to insert the number 20 into a tree. Alright, and here's my code. So it says struct node star temp. And if root equals null, well, root is equal to null. So what am I going to do? I'm going to malloc a new node, right? So I'm going to make this node temp, which is a new node. I'm going to set it data equal to num, which is 20. And I'm going to return that temporary node as the value of my insert function. So my main program, which said insert null, comma 20, gets back this. Alright, so let me do my main program. I'm going to set root equal to null. And I'm going to say insert root, comma 20. And at this point, when I come back, my root just looks like the node 20. Okay, so now I'm going to insert a 10. So let's see what happens when we call the insert function. So here's page 1. This is called from main. I'm calling it with a root which looks like this. And I'm passing the number 10. And what I want to do is just see what this set of code will do. Right, we're going to try to track its recursive behavior. So it declares a variable temp, which we haven't initialized yet. And it says if root is null, do some stuff. Well, root is not null. Root is pointing to a node containing a 20. So we're not going to do any of this stuff. Okay, if our number is bigger than root data, well, root data is 20, our number is 10, so it's not going to do any of this stuff. So we're going to do this last set of code. So we're going to say temp equals insert root left, comma num. Okay, so this step is in progress now. Okay, and we're about to make a call to insert. So this is going to get saved on the stack. Everything about this, the value of num, the value of root, the value of temp, that's all going to get saved, and we're going to make a new call. So I'm going to start a new page in my stack memory. This is page 2, and it's called from page 1. And I'm calling insert with root arrow left. Well, root arrow left is null, so here my root is null. And I'm passing it my number, and my number is still 10. So here's my first recursive call to insert. Trying to insert a 10 into a null tree. So if root is null, which it is, I'm going to set temp equal to a new spot. I'm going to set its data equal to number. So temp will look like this, and I'm going to return temp. So this call to insert is going to return a 10. Okay, I was called from page 1, so I'm going to go back to page 1. And temp is going to be set equal to whatever insert returned. Well, insert returned this tree containing a 10. So now temp is just this tree containing a 10. And we have finished our call to insert. And now it says root left equals temp. Well, here's our root, so its left child should change to temp. And then we're going to return temp. That's a typo. I should have fixed this before I made 20 million copies of this. So we're going to return root. Alright, so here's the root. So what do we send back here? We send back this tree containing 20 and 10. And so when we come back from here, root equals 20 and 10. Alright, let me fix my typos. Okay, so let's do one more. Let's insert. Well, let's start with a more interesting tree at this point. So we've got the null case where we go from an empty tree to a non-empty tree. So let's start with a more interesting tree. So let's suppose we have a 20, a 10, a 5, and a 15. So this is root, and we want to insert 13. Alright, so from main, this is called from main, so this is page 1, we're going to insert a 13, and our root looks like this. Alright. So if root is null, which it's not, so we skip this code. If our number is bigger than root data, well, root data is 20, our number is 13, so we skip this code. So we're going to call insert root arrow left comma number. So we're going to make a recursive call. And let me start a new call frame. So page 1 is going to make a call to page 2. And we're going to insert our same number, which is 13. And we're going to insert it into root arrow left. Right, so we're inserting into root arrow left. Well, this is root, so root arrow left looks like just this 10, 5, 15. So there's 10, 5, 15. This is called from page 1. Alright, so what do we do? If the root is null, well, root is not null, it's a tree with 3 nodes, so we skip that. If our number is bigger than root arrow data, well, it is. Our number's 13, root arrow data is 10. So what are we going to do? We're going to call insert. And we're going to try to insert a 13 into root arrow right, which is this node containing a 15. So we're in the middle of this step right now. And let's make a new call frame. So from page 2, we're going to start a new stack frame, which is 3. We're passing it our number, which is still 13. But the root we're passing it is root arrow right. So this is root. Root arrow right is just a node containing 15. So now in this new call to insert, here's what we have. We have a root containing a single node 15. We have a number 13, and we're trying to insert it. So if the root is null, well, it's not. If our number is bigger than root data, well, it's not. 13 is smaller than 15, so we skip this. So we come down to this last section, and this makes another recursive call to insert, which says insert our number 13 into root arrow left. Well, this is root. Root arrow left is null. So let's go ahead and make that recursive call. So we're on page 3 right now. So we're going to start a new page 4 called from page 3. And our root is the left subtree of this, which is just null. Our number is the same number that we called that frame with, which is 13. And now we execute the code and insert. And first thing it says is if root is null. It is null. So we're going to execute this statement down here. We're going to allocate space. To make a new node, we're going to set the data value equal to our number, which is 13. And we're going to return that temporary node as the value of insert. All right, where do we return to? We return to call frame 3, page 3. That's right here. So there's page 3, and what did we do? We said insert, root left, num, take the return value from that. Well, what was the return value? It was, the single node containing a 13, and this says set temp equal to that. So temp becomes a 13, and then this says root left equals temp. So root left becomes a 13, and then we return root. So the return value from this call to insert is this tree. And we were called from page 2, so let's go back to page 2. And what was in progress was this call to insert. We've just come back from that, and it says set temp equal to the return value. Well, the return value was this tree right here. So now temp looks like this. And this says set root right equal to temp. Well, here's the root. So this says set its right child equal to this thing. So the right child looks like this. And then return root. So this is going to return this tree. And we're going to return to page 1. So we go back to page 1, and where were we? We were in the middle of this call to insert. We've gotten back from insert, and this says set temp equal to the result of that call. Well, the result of that call was this little 4-node tree. So now temp looks like this. And we've done this statement, and now it says set root left equal to temp. Well, here's the root of our tree, so we want to set its left child equal to this thing. So it'll be a 10, a 5, a 15, and a 13 hanging off here. And then return the root. So this call to insert will return this tree containing 5 nodes. And that was called from main. This was our original call to insert. And the return value from that is this tree with 5 nodes. And so if in main we said root equals insert root comma 13, now that's what root looks like. All right, so that's a picture of the actual recursion going on in this routine. I don't know if that helps or not, but that's another view of it. And we are out of time. All right, so I will see you in class for 2:15, or I will see you next week. All right, cool. Have a good one. Thanks.